Section 8.2 confidence intervals for one population mean when sigma standard deviation is known. We're going to find out later on for one population mean when sigma is unknown. And then we're going to later on look at two population means. That's why we call it one population mean here. Because in later chapters, you're going to look at two population means. Now, before we start with this, let's recall from previous sections that 1 minus alpha, we call it confidence level or level of confidence, where alpha is always between 0 and 1. And so, for example, if the confidence level is 95%, it's like I'm 95% sure that this works out, then alpha, how do you find alpha? Alpha is going to be 1 minus the 95%, which is 0.05. That's the first thing we need to recall. Number 2 to recall is the z-score. So z sub alpha is the z-score that has an area of alpha to its right. Under what? Under the standard normal curve. Under the standard normal curve. That's what it is. So for example, if we have something like this, that means this represents the z-score, the z-score that has an area of 0.05 to its right. So z sub alpha over 2, also the z-score that has an area of alpha over 2 to its right. And important note here, for any normally distributed variable, we have 100 times 1 minus alpha percent of all possible observations. Observations, those are like the data values, lie within alpha z sub alpha over 2 standard deviation to either side of the mean. So our goal here is to find the confidence interval for the mean when the standard deviation is known. Okay, when the standard deviation is known. So if we look back up here at this, so here it says approximately 95% of all samples means within 2 standard deviation because of the empirical rule. And this is the one that I just wrote, 100 times 1 minus alpha percent of all sample means fall within z score of z sub alpha over 2 standard deviations of the mean. And to represent this on the graph, as you can see, the first line represents x bar, the mean, and that's the 95%. This is the 1 minus alpha, and then if you take the rest of what left from 100%, so 100 minus the 0.95, that's 0.05, and if you divide that by 2, that gives 0.025. That's why we have 0.025 on each side by symmetry. And this is actually representing this is within 2 standard deviation from the mean. So it's mean minus 2 times standard deviation sub x bar. But that one is the same as the mean minus 2 times this over the square root of n. Same thing for the other one. And on the standardized curve, let's draw a line here. That's the Z1. The mean is 0, and then 2 up and 2 below, 2 above and 2 below the mean. Okay, and how are we going to construct the confidence interval? We are going to use table 2 to find. So we use table 2, as you can see here, use table 2 to find Z sub alpha over 2. And then from there, they give us the mean, they give us standard deviation and the sample size. And we substitute them into these two expressions, here. That will give you the lower bound and the upper bound of the interval. We can look at an example here. We can look at an example to see, maybe let me do an example here. Let's say we have 95% confidence, level of confidence is given. The sample size N50, the standard deviation 12.1. So first thing I do, I find alpha, which is 1 minus the 95%. That gives us 0.05. And the mean, let's say the mean is given as 41.4. Okay, they give us the mean. Now, how do we find Z sub alpha over 2? We do need Z sub alpha over 2. So that would be Z sub 0.05 over 2, Z sub 0.025. And now we go to table 2 and see what you find out. In table 2, you need to look in the body of the table, and see the value here that has this value. That's the area goes in the body of the table. And then you go this way and up, you're gonna find it's gonna be 1.9, and there's 0.06. So it's 1.96. That's Z sub alpha over 2. That's the Z score corresponding to that area. So after we find this, we go back to the two formulas, the x bar minus Z sub alpha over 2 times the standard deviation over the square root of n. X bar is given as 41.4. This is 1.96 times the standard deviation was given 12.1 over the square root of 50. So that gives us 38. And similarly, we do the same thing for the plus Z sub alpha over 2 times the standard deviation over the square root of n. So x bar is 41.4 plus 1.96. This is 12.1 over the square root of 50. And then if we run the calculations out, you can calculate this one first and multiply the result by 1.96 and add that to this. So this is the last thing to do, is to add the 41.4 and try it. You will get 44.8. So this means the interval would be from 38 to 44.8. Okay, if in case you take you increase the level of confidence or the population, this interval will get bigger and bigger. That will get bigger and bigger. Now, since we are not 100% sure, there's, as we said in the previous section, there's a margin of error. We use E to represent the margin of error. Now, from note, the x bar plus or minus, I'm going to say Z sub alpha over 2 times the standard deviation over the square root of n. You can rewrite this. Remember how when we did the previous section, I wrote x bar plus or minus 2, and I said the plus or minus 2 was a margin of error. So then that is E for error. So then this means we can say E, the margin of error, is represented by Z sub alpha over 2 times the standard deviation over the square root of n. Okay, and if I want to find it for this previous example, so find E, which we already did actually, it's Z sub alpha over 2 times the standard deviation over the square root of n. Z sub alpha over 2, we found it was 1.96, and the standard deviation was 12.1 over the square root of 50, and that gives us 3.4. So let's say, again, I'm commenting back on the interval. If we reduce the level of confidence to 90, let's say, I did run some calculations here as well. If we do 90% confidence, then the interval, it will be 38.6 to 44.2. So it's a smaller interval. How do you know this one is smaller than the other one? Just subtract the values. Subtract this minus this, and you see what you get, the width of the interval. Same thing for this one. You'll find the longer the width, the better, the bigger the interval. So if we reduce the level of confidence, then it will be, if we reduce the level of confidence, we will get a smaller interval. The larger the interval, remember, the better. So this is the margin of error representation on the graph, so you can see it. Now, from all of this, is it possible to find n, like the sample size, if some information are given to us? So yes, there is a way to do that. And what is the way is, from that equation, we can solve for n. I'm not going to do it here, but you can divide and or cross multiply and then divide, then square. You will get an n formula for n, which is z sub alpha over 2 times the standard deviation over the error square. This is the sample size formula. Okay, so that's sample size formula that we can use. And always, when you get an answer, always round to the nearest whole number. Round to the nearest whole number. That's important to keep in mind. So if I want to apply an example to this, let's say we go back to the 95% confidence interval level, and then we found z sub alpha over 2, the z score 1.96, where, let's say, the population mean is within 0.5 of the point estimate x bar. So now how do you find n? What is n? Well, we said n is given by z sub alpha over 2 times the standard deviation over e to square. So what is z sub alpha over 2 is given 1.96 times sigma here is 12.1 over e. When they say within that means the error 0.5, and we need to square this. So to do this, you first multiply these two numbers up, divide the result by 0.5, and square the final result. That gives us 2249.7, which can be approximated as 2250. And then you will see the formula here again, and it says round to the nearest whole number.